any further ado, let's move on. So our first speaker is going to present to us, I believe, the Hearst building in New York, which is a tremendously interesting and exciting building. It's certainly on many, many magazine covers. And I will turn it over to Bart Sullivan, who's going to give us insight into that building.
Okay, thanks, Ron. Good afternoon, everybody. Originally, Rahimian of Cantor Seinuk was going to give this presentation. Some of you who have the older programs might see his name on it. And you're thinking that guy up there doesn't look Iranian, you're right. I worked with Ahmed for many years in New York. Now I'm based here in Dubai. And Ahmed is really the person that really deserves a lot of the credit on this project and bringing forth a lot of the innovative ideas and really creating a successful project. So I'm basically going to go through the project as sort of a structural case study. It's also a big part of this building in terms of sustainability and the more to do with the mechanical, electrical, plumbing systems. And if any of you track down Gary Pomerantz of WSP Cantor, he could give you a whole oration, which is a totally different talk on that topic as well. To start off with a few of the facts about the project, it was commissioned by the Hearst Corporation, and they retained Tischenspire to be the development manager, and they organized the design team of Foster and Partners as the architect, and Adamson Associates as the associate architect, WSP Cantor Seinuk, and WSP Cantor as the structural and MEP group. The building is a 42-story building. It's nearly 600 feet tall, so it's a bit tall for that many floors, given the base of the building is projected up, and over 850,000 square feet of buildable area. The story of the Hearst building really starts back at the turn of the last century when William Randolph Hearst started buying up property around 57th Street and 8th Avenue in New York City. And they commissioned this building in 1926 to be designed by Joseph Urban and George P. Post and Sons, and it was first occupied in 1928. It has a very unique limestone facade, which is sort of fitting to a media mogul's headquarters, in that it has these unique allegorical figures around the perimeter of the building that represent music, art, commerce, and industry, and it has these spires that you see around the perimeter as well that sort of hint at something more to come in the future. Actually, the building was designed to hold an additional 7 stories on top, but by the time 2001 rolled around, and they actually needed more space. They needed quite a bit more than just 7 stories of the building. So this facade was recognized as an important part of the New York City streetscape and was designated as a landmark for the city in 1988. So the development of this project meant that you had to retain this facade intact. Anything within the building could be taken out, but the facade itself had to be maintained. The building, as I said, was on the west side of New York City, between 56th and 57th Streets. It's a horseshoe-shaped building. It's bounded on 3 sides by streets, and on the west side of the building it has a adjacent high-rise building right on the lot line. So given this arrangement, the new tower was thought to be placed hard up against that west lot line as well in order to maximize the viewing space out to the street and maximize the window space for the offices around the building. So what this did was it ended up creating an eccentric core to the building, which was also pushed to that west side. As in most high-rise buildings, or many high-rise buildings, the core is really an obvious place to create a lateral system for the building, and it's no different here. The only issue is that it was pushed eccentric to the building. So we had to find a way to create a lateral system that was more balanced. And originally the idea of the building, these are some early sketches by the architect on the outside of the building. It was basically vertical columns and more ordinary traditional type building system. But we started to explore how we could manipulate the east face of the building and create a more or a less eccentric lateral system to the building. So we started off looking at moment frames, super diagonal, different configurations, and finally landed on this diagrid system that you see all the way onto the right. And together with the architect, and the architect liked this idea, and so this is how we brought it forward. So it was really, it wasn't something that the architect had a preconceived notion about. It was really something that was organically developed through the design process between the structural requirements and the architectural parameters of the building and the site of where the building is located. It all grew out of that in reality. One of the issues also with the diagrid system is that with the nodal points at 40-foot spacing, you ended up having a 20-foot cantilever at the corners of the building every floor. So this became a bit of a problem in terms of deflections and vibration issues that you would have to overcome at the corners of the building. And then this was what drove the bird mouth corners of the building where they're actually carved out at the corners. So I think this is really the way successful projects really should be brought about, and that you have a meeting of the minds of all the different team players and really creating something that works for everybody in the building. And I think this job shows that it really was done quite successfully. At the base of the building, the exterior facade, as I said, it has to remain intact, but they wanted to create a really open environment here, an atrium space at the lower areas for cafeteria and meeting spaces, and a place for the employees of the company to really come to relax. So what we had to do was actually go through a similar type of study for the base of the building, where we looked at different ways of creating this open space and bringing the building down through that space and trying to open it up and looking at different ways that was possible to do. We finally settled on a mega column system whereby each of the diagrid elements would be collected into a large mega column element, which is a large steel box section which is filled with concrete. And these are the elements that you see in blue down towards the bottom, and also super diagonal elements that would divert the interior local columns out to the edges to create that open space. And at the same time, since we're losing that diagrid system and that lateral system down below, those super diagonals also help the core in resisting lateral forces on the building too. So just to give you a quick recap on the sort of lexicon of the building, you have the diagrid elements that come down and sit onto the mega columns. The interior columns come and down onto the super diagonal elements and get converted out. And then you have this landmark facade, which is braced basically at the top and the bottom, and it has to span between those two locations. And I'll talk a little bit more about that down a little later in the talk. One of the main issues with a diagrid system or a super diagonal system is the unbraced length between the nodal points of the diagrid. You need to create some sort of secondary system by which you can provide stability in between those nodal points. So the way this was done was to create concentric braced frames at all the floors in between those nodal points. And obviously this is done at the core area of the building. The core was also encased down at the lower portions of the building, where we have a diagrid, where we're stopping the diagrid and encased in concrete as well to add more stiffness to the building in that area. And you might ask, why not just build a concrete core up the entire height of the building? And this sort of comes back to something that's very particular to New York City, where the labor laws don't allow the iron workers to work below any of the concrete work overhead. So the steel structure has to go up first. So you don't see anybody slip-forming cores in New York City. You only see a steel erection going up prior to the concrete. So this was the system that we came up with, and you see here in the background, you see the core element going up with the bracing, and this provides a temporary braced element for the rest of the building to go up during construction, as well as the final condition too. Getting back to the idea of this secondary bracing system, one of the important aspects to look at in a system of this nature is the buckling modes and the macroscopic buckling of the building. And these are just showing a few tables of the first few buckling modes of the vertical elements in the building. this is an important consideration for buildings like this, and it's something that is not necessarily thought about every day. And that this can be, depending on the situation, the controlling design case in the building. Many engineers might think that just because you've created a lateral system for the building that works for a given wind load that it's okay, but really you have to take a look at this key design check for a diagrid system or a super diagonal type system. So what we settled on was a concentric brace frame in one direction, which just shows a few of the elevations, and an eccentric brace in the other direction around this core. Eccentric braces in order to allow access to the elevator lobbies and so forth. One of the other issues that's particular to a diagrid system is the deformation of that diagrid. And this is just a table, don't have to read the numbers, but basically they're just the deflections of the building in the 3 dimensions in the X, Y, and Z direction, just under a gravity load. So you have to pay careful consideration to the way this whole thing is going to move much differently than a traditional straight vertical column system. And particularly this is important for the cladding design of the building and the way that these nodes will move in and out, particularly if you have an unsymmetric building like in this case. So early in the design process, we really had to think a lot about the architectural intent of the building, and this is showing a model of the building, the original architectural model, where they're really looking to get crisp lines in the buildings and clean corners that aren't any bigger than the main elements themselves. So the goal was to create these nodal points without large gusset plates that would get in the way of the architecture, because that basically, in a way, it destroyed the elegance of the building and the architectural beauty of the building. So early on, we started looking at 3-dimensional models. Now, we all have computers in our office and we can build these things on a computer, but really I don't think that anything really substitutes for physically seeing that model and building something to understand how the thing works and how it can be put together. So we looked at a variety of different ways of creating these nodal points that were quite tight and compact. And what we settled on was this system of sort of a steel block, if you will, that was created of 2 large thick plates and put into several different configurations. This is just a couple of the details. You see the shaded area, or these thick steel plates that transfer the wide flange elements that create the diagrid system and bring it down into this plate and then back out. So there are a variety of different conditions and the transfer of the diagrid system down into the mega columns below, all done in a similar fashion, creating these compact solid steel elements. And another important part of this whole development is really getting the contractor in on board early and talking to steel fabricators. And we showed them these things, and we showed them the models, and sat down and reviewed these kinds of things with them. And it's really essential to get them on board at the very beginning, so that you're not creating something that's so elaborate that's really quite new without somebody else's input on who's actually going to build the thing. And they embraced this idea, and we took it forward. This is showing just another condition in the building where we have the mega columns coming down and the super diagonals coming into that mega column. And there's a large offset force into the horizontal force into the floors, so we had to create stiffening brace elements of the diaphragm to transfer those loads through the floor plates and balance it out. Coming to the landmark facade, this was really another challenge in and of itself. It's a whole other project in essence. The facade had to remain intact, but nothing inside needed to stay. Nothing inside, they didn't want anything inside to stay. It was all going to be a new space. So the challenge was to come up with a system that would work in a temporary condition and a final condition in order how to build this interior structure and leave that facade standing and intact. This is one of the early finite element models of the limestone facade. And the idea was that the facade would span from the 3rd floor up to the 7th floor in that atrium space. And this is a model of the building. It's a little difficult to perceive, but you see the vertical elements of the mega columns and the horizontal elements, if I can get the cursor up in this region. This is the glass facade of the top of that atrium space, and these small elements that come out brace the brace that top of that facade level. And the original building had a steel structure, a steel frame system, and so what you see in blue in this image here is the existing steel that's in the building and then holding up the limestone facade. So we looked first at seeing how we could span from third floor up to the seventh floor with this facade, and the idea was to have the limestone span between the steel structure and have the steel structure span up to these support points at the diaphragm levels. So this is sort of a simple diagram of moment diagram of a lateral load being applied to that face and the vertical steel elements bending. And this is just a stress diagram to show the stresses in the limestone elements themselves. And what we found was really that we really couldn't count on the existing structure just the way it was to support itself. It would just become overstressed. And that led then to adding in some additional steel framing in between the existing steel framing to support that facade. Now, and this is just really a detailed drawing of the actual elements being put onto the facade. So there's quite a number of elements that we had to put in, quite a bit of reinforcement of that limestone to be done. And that's a little bit easier said than done, obviously. And out in the real world conditions, when you want to put this steel in, you have an existing building there. You can't just walk in the door and start putting in steel framing. There's quite a bit in your way. So the first thing that was done was to put bracing into the first bay within the building to carry the stability of that wall. So what you see here is the vertical element is an existing column in the building, and all these diagonal elements are new bracing elements within that first bay out to the facade. This is right at the corner of the building. And so the entire inside of the building was gutted, leaving that first bay to brace the outer facade of the building and creating a working space inside. This is just a view from outside. And this is a view of the plot from the west side looking down from the adjacent high-rise building. So you see that there's quite a bit of congestion in this area, and to install these elements is not really an easy task. So what we really try to do is to create a system of small elements that can be handled relatively easy for the contractor, and so that he can install them into the facade wall and then remove this space and when the permanent building comes in. One of the other points about the building, this foundation system, is that, as many of you might know here, or many of you might not, the ground conditions in New York are generally pretty good. There's bedrock very close to the surface of the roadway, and it's usually relatively easy founding material. But in this case, the rock formation had a big slope in it. So at the west side of the building, here you see a piling rig. We had caissons put in at the west side of the building. The east side of the building, we had spread footings directly onto the bedrock. So there was some amount of work in dealing with differential shortening of these two foundation elements to make sure that the building was straining evenly. And just to go through a little bit of the images of some of these heavy elements, these are some of this 5-inch thick steel node plates that were used for the connections of the diagrid. This is one of the mega column super diagonal joints with the diaphragm bracing connections put onto them as well, and to get a little bit of feel for the size of some of these things. They're not the easiest things to throw around. And then we had some more traditional connections in the core area where it wasn't aesthetically necessary to really do anything fancy with that. And this is just showing some more of the floor framing of the building with the slots for the MEP in order to minimize the depth of the floor sandwich as well. Just going through some of the construction of the building, these are the super diagonals coming into place in the podium area. Some of the quite large connections. In general, we try to create a lot of bolted connections in the building, but in some cases it's just, it's really just not possible. And some welding has to be done for some of these really large elements in order to create these clean shapes that they architecturally you want to express within the atrium space in particular. So here we just see some of the building coming up out of the existing facade. And this was the first diagrid node that was put in. And these two guys, I think they paid a lot of money, well-deservingly. This is a shot from above of the atrium space below, and you see again the brace elements here that are bracing the facade out on this line here. One of the interesting things with the curtain wall was the actual formation and the expression of these diagrid elements that the architect was trying to express throughout the whole height of the building, not just a sort of a flat facade, but that really presents some difficulties in creating an effective facade system for the building. So really, the entire building is all the diagrid system is actually within the facade line of the building, and you see that actually these panels that create this beveled edge are brought on afterwards and placed on top of the glass facade. And these are just a few more construction photos of the building going up. One more item is this object-oriented three-dimensional software that we have these days, which is really starting to come more into play now. And it's really a great thing for a project like this, especially not just dealing with every single bolt and plate in the building, but also in things like when you have a less than simple facade like on this system, that you can actually model all the mullions and the connections of the facade elements to make sure that you have a coordinated and system. These are just some of the mock-up panels of the glass and the facade of the building going up during construction. So thank you very much.